Alright, so we are discussing the importance of local rings, okay, and what we saw in the last lecture was that we've seen two theorems which tell us the importance of local rings. So the first one was that a morphism is an isomorphism if and only if it is a homeomorphism and induces isomorphisms at the level of local rings. So that is a characterization of isomorphisms in terms of local rings, okay. Then the other thing that we saw was we saw that a rational function, okay, an element of the function field of a variety, namely a function which may be defined only on a proper open subset, that can be I mean you can ensure that it is actually a global regular function if and only if it occurs in every local ring considered as a subring of the function field, okay. So in this regard, what I wanted to tell you is that there is this algebraic fact, it's a simple algebraic fact, and this is what we proved last time. You see, if A is an integral domain, and then of course A is contained in its localization at any maximal ideal, okay. So max spec A is the set of all maximal ideals of A, okay, and of course every integral domain is contained in its localization at a maximal ideal. This map A to its localization is just the localization map, okay, and it is injective, and that is why we consider A as a subring of the localization of A at M. And further, this is contained in the quotient field of A, which is the same as the quotient field of A of the localization of A at M, okay. So this is so what this tells, I mean this always happens, alright, and what this tells you is that A is contained in therefore the intersection of all the localizations at various maximal ideals inside the quotient field, okay. But the fact is that this is actually an equality. If you go through the proof of the statement that we made last lecture, that a rational function is a global regular function if and only if it occurs in every local ring, okay, then actually we have if you see that the commutative algebra that we did there, the proof, actually proves this, that if A is an integral domain, then A is exactly the intersection of all its localizations at various maximal ideals, the intersection being made sense of in the quotient field of A. So so this is a completely algebraic, commutative algebraic fact, but it has a geometric meaning. The geometric meaning is that if you take for A if you take A to be the affine coordinate ring of an affine variety, okay, then this quotient field of A is nothing but the function field of the variety, and you are saying an element of the function field which is in every local ring has to be a global regular function, okay, because the AMs will then be the local rings at the points AM, for example, will be the local ring of the variety with the affine variety with coordinate ring A at the point corresponding to the maximal ideal M, okay, and the fact that the intersection of all these local rings is A is a nice statement that when you translate it geometrically, it means that a rational function which is there in every local ring is actually a global regular function, okay. So so basically I just wanted to point out that this is an algebraic fact, but it has a geometric meaning, okay. The geometric meaning is that a rational function which is in every local ring is actually defined everywhere, it's a global regular function, right. Okay, so now what I stated at the end of the previous lecture was a fact about birationality. So let me again recall that statement. So this is yet another nice result that tells you about the importance of local rings. So the result is that if you have two varieties which may not be related at all, but suppose I know the local ring of one variety at one point is isomorphic as K algebra to the local ring of another variety at another point, then the deep result is that these two varieties are isomorphic on open subsets containing the respective points, which we call as birational, okay. So just isomorphism of local rings produces an isomorphism over a large open set, because open sets are all large in the Zariski topology. So this also tells you that the local ring is not so local, it also contains a lot of global information, okay. It contains information on a large open set, and that is in a way inevitable because in the Zariski topology all open sets are huge because they are all dense, any open set is dense, okay, for a variety. So of course any non-empty open set. So let me write this down. So theorem, let X and Y be varieties with x, small x a point of capital X, small y a point of capital Y, and an isomorphism of K algebras from the local ring of X, capital X at small x to the local ring of capital Y at small y. So this is maybe I can call this as I do not know what I called it in the last lecture, so let me call it as phi, okay. I do not know what did I call it, I called it psi, okay. So let me call it psi, let me use the same notation. So I have these two varieties and I have points where the local rings are isomorphic by a K algebra isomorphism psi, okay. Then there exists open subsets U of X, V of Y with X in U, Y in V, such that, and an isomorphism of varieties phi from U to V that takes so that X goes to phi of X is Y, okay, X goes to Y, and which induces via phi hash. So I will get a map from the local ring of V at y to the local ring of U at x, and this map is phi hash sub y, okay. And mind you, the local ring of V at y is the same as the local ring of y at capital Y at small y, because the local ring does not change if you go to an open set, and similarly this is the local ring of capital X at small x, okay. So phi is an isomorphism of varieties, therefore this will also be an isomorphism, and the fact is that this isomorphism is none other than psi inverse, okay. A K algebra isomorphism given K algebra isomorphism phi hash y equal to psi inverse, okay. So in other words, any isomorphism, so what I am saying is, you see, if a local ring of one variety at one point is isomorphic to a local ring of another variety at another point, then that isomorphism is actually induced from an isomorphism on open subsets of an open neighbourhood of U of the point small x and an open neighbourhood V of the point small y. They are isomorphic, okay. So the isomorphism of local rings comes from an isomorphism of huge open sets which contain those points. So in other words, see, isomorphism at the local ring, actually if you think of local ring as concentrating attention at a point, what you are saying is that the isomorphism of these local rings has, I mean, it can actually be spread to an isomorphism on open sets, okay. So that is the power of so you know, so and you know, when we have two varieties which have which are isomorphic on open subsets, okay, then we call those varieties as birational, and what we are saying here is that of course if two varieties are birational, then there are going to be local rings here which are going to be there are going to be isomorphic local rings, okay, wherever the isomorphism is defined. But conversely, if you want two varieties to be birational, all you require is one isomorphism between local rings, okay. So that is the power of local rings. So let us try to prove this fact. So the proof also involves just commutative algebra and several facts that we have already seen. So here is a proof. Well, so the first, so what is given to me is that I am given x, I am given y, and I am given a point small x in capital X, and I am given a point small y in capital Y, okay. And what I am given is at the level of local rings, I am given an isomorphism. So well, if I draw the diagram corresponding to this here, I will get well, x corresponds to OX and y corresponds to OY. So you see here I am writing the well, if you want, this is the geometric side and this is the algebraic side, okay. So then I have, corresponding to this point x, I have the local ring OXX, O capital X small x, and here I have O capital Y at small y, and then I have this isomorphism which is given to me as psi. It's a K algebra isomorphism, okay. This is what I have, alright, and what I am supposed to do is I am supposed to find an open set U here which contains x and an open set V here which contains y, and an isomorphism between U and V which induces at the point x this isomorphism, okay. So the first fact I will use is that any variety is covered by finitely many open subsets which are isomorphic to affine varieties. Okay, so what I will do is that I will, instead of x, I will look at x1 inside x, where x1 is an affine open, x1 is an affine open which contains the point small x. Okay, and similarly I can find an affine open y1, I can find an affine open y1, an affine open subset of y which is affine open means that it is an open subset of y which is isomorphic to an affine variety and which contains the point small y. Okay, so here I am using the fact that we have proved earlier that any variety can be covered by finitely many open sets, each of which is isomorphic to an affine variety, right. And well, what happens to this diagram on this side? See, I will have this. So what you must understand is that there is this inclusion of the regular functions are included in the local ring. Okay, and in fact what will happen is that if you go to O, if you go to Ox1, that will sit inside, that will sit in between. Okay, because for any variety restriction of regular functions then is an injective homomorphism. Okay, because if I have a regular function on a bigger open set, I can restrict the regular function to a smaller open set, and this restriction is injective because if two regular functions agree on a smaller open set then they agree on the bigger open set. Okay, so this will and mind you this Ox1 will be, well, it's going to be Ax1. I can write Ox1 equal to Ax1 because x1 is affine, and well I have the same kind of situation here. I have Oy1, this is sitting inside this and this is a subring of this, and this is the same as Ay1. Okay, and of course and what about the local rings? See, the local ring of x, capital X at small x, will be the same as the local ring of capital X1 at small x, because the local ring will not change if you go to an affine open set. And then in this identification with Ax1, this local ring is going to correspond to some A. So let me do something, let me call this as A. Yeah, I must have had a little bit more space to write things, so let me move part of this diagram to the left side so that it's easier. So here is y, and here is y1, and here is small y. Okay, so so this Ax1, let me call it as A, let me call Ay1 as B. Okay, and see, what you must understand is that this x1 is an affine variety, therefore this x1 can be embedded into some affine space, into some an. Okay, of course we are working over small k, which is an algebraically closed field always, and similarly this y1 will sit inside some am. Okay, so so when I write like this, what I mean is that x1 is isomorphic to an open a closed irreducible closed subset of an, and y1 is isomorphic to an irreducible closed subset of am. Okay, and therefore what you must understand is that the points of x1 will correspond to maximal ideals in A, and the points of y1 will correspond to maximal ideals in B, and the point small x will correspond to a certain maximal ideal, and the local ring will be just A localized at that maximal ideal. Okay, and where the maximal ideal M corresponds to the point small x. Okay, in this identification of capital X, capital X1 with max spec A. After all, max spec A, set of all maximal ideals in A by the Null-Stern-Satz is identified with the points of x1, because A is A of x1, alright, and similarly the so x corresponds to the point s small x in capital X1 corresponds to a maximal ideal M of A, and the local ring is then just the localization of A at M. Okay. Similarly y corresponds to a maximal ideal neta, which comes again by this correspondence due to the Nullstellensatz. I have max spec of B. The maximal ideals of B correspond to points of y1, okay, and the point small y of y1 corresponds to this maximal ideal neta, and therefore the local ring here will be the same as local ring of y1 at y, and that can be identified with B neta. Okay, so we have already seen this. The local ring of an affine variety at a point is just given by taking the localization of the affine coordinate ring, namely the ring of regular functions, at the maximal ideal that corresponds to that point, right. So so basically, you know, at the end of all this, my diagram, and you know, what I am going to do is I am going to find an open subset of x1, and I am going to find an open subset of y1, and I am going to find an isomorphism between them, okay. And you must realize that that's good enough, because an open subset of x1 is also an open subset of x, and an open subset of y1 is also an open subset of y, and therefore you have also found an isomorphism between an open subset of capital X and an open subset of capital Y, okay, which contain the points x and y, okay. So in other words, you know, to say it in simple words, without loss of generality, I could have assumed that x and y are already affine, okay. So anyway, so my you know so my diagram is now so I simplify my diagram. So I have this A, and I have this B, and I have A sub M, I have B sub N, and I have this psi, which is an isomorphism of local rings, okay. This is the situation now, and well, you know, I'm therefore looking at only the I'm only looking at the affine case. So so here in this, so on this part of the diagram, you know, so let me put a line here and look at this part of the diagram. I have x1, I have y1, x1 corresponds to A and y1 corresponds to B, right. So I have this situation. Now what I want you to understand is that the what about see, if you look at quotient field of A, this is the same as the quotient field of AM, okay. The quotient field of A is the same as the quotient field of AM, and what is it? It is the function field of x1. So this is just kx1, okay. And similarly here and of course A sits inside its localization, and the localization sits inside its quotient field, okay. Similarly B sits inside in its localization, and that sits inside in the quotient field of B, which is the same as the quotient field of B neta, which is the same as the function field of y1, okay. So this again uses the fact that the function field of an affine variety is just the quotient field of its ring of regular functions, okay. So x1 is an affine variety, its ring of regular functions is A, which is also the affine coordinate ring of x1, and if you take its quotient field, what you will get is a function field of x1, okay. And the function field of x1 is of course the equivalence classes of rational functions, where rational functions are regular functions on open subsets, okay. So now what you must understand is that whenever you have an isomorphism between two integral domains, then it will automatically induce an isomorphism of the quotient fields. If two so this is very natural fact which comes out of the, if you want, the universal property of localization, or the universal property of the quotient field, which says that given a ring, given an integral domain, its quotient field is the smallest field which contains the given ring. named, so if the ring is embedded in another integral domain, okay, then if the ring is embedded in another field, okay, then its quotient field will also get embedded in that field. So the quotient field is the smallest field in which an integral domain can sit, okay. So because of that property, psi will induce an isomorphism here. I will call this as I will also call this as psi. So maybe I will so let me write this as induced by psi. This is just induced by psi, okay, and this diagram commutes, okay. So what you must remember is that it's even very easy to see what this map is, okay. What is an element here? An element here is a fraction, the numerator an element of A and the denominator an element of A which is outside M, okay, and that is how an element here looks like. And what you will have to do is, if you go to the quotient field, the quotient field is simply quotients of elements of A with the denominator non-zero, okay, but you can represent such a quotient as a quotient of two quotients here, okay, by taking the denominators as 1, and then you can define what this map is simply by using this map, okay. So it's pretty easy to see what this map is. It's straightforward to define, okay, even if you don't want to worry about the universal property and things like that, okay, you can directly write out this map. It's the most natural map that you can think of, okay. So this isomorphism induces this isomorphism, okay, and now what we are going to do is, now we are going to make use of the fact that that these two are affine, okay. So you see A is, well, A is what? A is the affine coordinate ring of x1, it's the ring of regular functions on x1, and that is the polynomials in An, the polynomial functions on An restricted to x1, okay. So A is just k of x1 etc xn modulo the ideal of x1, okay. This is the affine coordinate ring of x1, right, and similarly B is the affine coordinate ring of y1 is embedded in Am, okay. So B, which is the affine coordinate ring of y1, is just the polynomials in Am, okay, polynomials in M variables restricted to y1, and that is given by k of y1 etc, okay. So there is a conflict of notation somehow, so let me, okay, so I have conflict of notation. My x1 is also a variety and my x1 is also a variable, so it's a pity. So let me do the following thing, let me change this to something which is more decent. So let me use s1 etc up to sn, where si are the variables coordinates, and here let me use t1 etc tn. Divided by ideal of y1, okay. You must remember that this ideal of x1 is the ideal inside this, okay, it is the ideal in An, and this is the ideal of y1 inside this, which is in Am, okay. This An here is taken with coordinates s1 through sn, this Am is taken with coordinates t1 through tm, so this is tm, okay. So here the coordinates are s1 sn, and here the coordinates are t1 tm, okay. So that is the situation, and now you see, now what I am going to do is I am going to look at so you know this A is generated by the images of the SIs, okay. Therefore I am going to look at what happens to the effect of psi on the SIs, and I am going to also look at what happens to the effect of psi inverse on the TIs, okay. So the situation is like this. I calculate, so let me write here, calculate psi of let us look at psi of SI bar divided by 1. Okay. So what you must understand is Si is an element in this polynomial ring, okay, it is a variable. In the quotient you get Si bar, okay, and if you go to the localization you write it as Si bar by 1. So the natural map from a ring to its localization takes any element of the ring to that element divided by 1, okay. This is the standard map into any localization, right. So any element here alpha will go to alpha by 1. So if I take the element Si bar it will go to Si bar by 1, so I am looking at it here, right. But then you can treat Si bar by 1 also as Si bar itself, because if you think of everything as happening in this quotient field I do not have to write this divided by 1, but anyway I will write it so that you remember that I am taking its image here and I am applying psi to it, right. So now what is this? Now the image of this is going to be something here, alright. So but something here is a fraction, it consists of a numerator and a denominator. The numerator is an element of b, the denominator is an element of b which is not in neta, in the maximal ideal neta. So what I am going to get is I am going to get Fi bar by Gi bar, okay, where of course Fi bar and Gi bar are just polynomials in the Tj's, okay, and the Gi bar is not in the maximal ideal neta that the maximal ideal neta of B that corresponds to the point small y, okay. So let me write that Gi bar does not belong to neta, okay. So what you must understand is if Gi bar is Gi bar is not in neta, therefore so 1 by Gi bar makes sense here, 1 by Gi bar makes sense here, because it is after all an element which is inverted. What is B sub neta? B sub neta is take all the elements of B and then you divide, you allow fractions where you invert things which are outside the maximal ideal neta, and Gi bar is not in neta, so 1 by Gi bar makes sense in B neta, right. But then this 1 by Gi bar lives here, okay, so it has to come from something there, because after all psi is an isomorphism, okay, and so I can look at those elements here. So let me write Fi bar of Tj by so I will just put Fi bar of T by Gi bar of T just to remind you that the Fi's and Gi's are polynomials in the T's, okay, and and of course something here will be a polynomial in the S's, okay. So so you let this, and also you let psi inverse of 1 by Gi bar of T to be something here, and that something there is going to be an element in here, okay. And if I write this as well, let me write this as Ai bar, Ai of S bar by Bi of S bar. When I write S I mean the tuple of variables S1 through Sn, and when I write T I mean the m tuple of variables T1 through Tm, okay. The things on this side are all polynomials in the S's, and the things on this side are all polynomials in the T's, and if you go to the level of quotient fields, here the things on this side are essentially thought of quotients of polynomials in the S's, and here the elements are quotients of polynomials in the T's, okay. So now what I want you to understand is that see, whenever you have an isomorphism of local rings, okay, then a local ring has only one maximal ideal, okay. So whenever you have an isomorphism from one local ring to another local ring, then under an isomorphism the image of a maximal ideal is again a maximal ideal. Therefore what it means is that the maximal ideal of this local ring, the unique maximal ideal of this local ring, has to be carried by this isomorphism onto the unique maximal ideal of that local ring, okay, and that means that an isomorphism of local rings will give an isomorphism of the corresponding maximal ideals. And the fact that 1 by gi bar is the fact that, you know, so I want to say that this when I write this expression, okay, I want to say that this fellow here is invertible, okay, because you see gi if you want 1 by gi bar of t is a unit here, 1 by gi bar of t is a unit here, because gi bar is the gi bars are outside the maximal ideal, therefore they all get inverted here, so it is a unit, and an isomorphism will carry a unit to unit, therefore it means that ai bar by bi, this ai bar by bi bar is a unit, okay, and since ai bar by bi bar is a unit, it means that both ai bar and bi bar are units, okay. So the upshot of this is that both ai bar and bi bar do not belong to the maximal ideal M here, okay, okay, where ai bar, bi bar do not belong to the maximal ideal there, okay. So this is an observation, right, this is an observation. So now let's interpret this a little carefully. Now you see somehow, you know, we have to go you know, you have at the level of small x, you have at small x and at small y, at the local ring level you have an isomorphism, you have to somehow lift it to an open set, so I have to go closer to x1 and y1, so which means that I will have to go away from the local ring and I have to come closer to this ring, okay. So you know, if you look at what happens to the image of psi, so the first thing is that you know, if I take you see the psi takes each si bar into an expression like this, alright, therefore if you take any element of A is a polynomial in the si bars, okay, because A is just polynomials in the si bars modulo this ideal, so any element of A can be thought of as a polynomial in the si bars, okay. In other words, we say that A is generated by the si bars, okay, therefore any element of A is a polynomial in the si bars, and if you take its image under psi, okay, then what I am going to get is a polynomial in these things with k coefficients, okay, and you can see that the denominators are given by the gi's, okay, therefore you can see very clearly that the image of A under the image of the subring A under psi lands inside this localization, namely B localized at the product of all the gi bars, okay. So there is this localization B, you invert all the gi bars, and the product of all the gi bars you will have a further localization, this will be an intermediate localization, because you see all the gi bars are not in eta, okay, all the gi bars are not in eta, and that means that the product of all the gi bars will also not be in eta, okay, because eta is a maximal ideal, so it is prime, therefore B localized at all the product of all the gi bars, which by the way is the same as inverting each of the gi bars, okay. So this is B localized at the product of all the gi bars, and that will sit inside a subring between B and B eta, okay, and the fact is that if you follow A by this, it actually lands inside this psi restricted to A, okay, psi restricted to A will land inside this, because after all what is an element of A, it will be a polynomial in the si bars, and if you apply psi to each si bar I am going to get fi bar by gi bar, so if I have a polynomial expression in the si bars I am going to get a polynomial expression in the fi bars by gi bars, and that is some polynomial divided by some product of gi's, okay, some product of powers of gi's, and therefore it will lie here, alright. So the moral of the story is that psi restricted to A will give you an injective K algebra homomorphism from this to this, right. And you know the point I want to make is that what have we done geometrically. See, geometrically what you have done is, you see, you have gone to each gi bar is a polynomial, is a regular function, okay. Each gi bar is an element here, but what are the elements here? The elements here are just regular functions on y1, okay. And what do you mean by inverting a gi bar? Inverting a gi bar amounts to going to the open set, the basic open set given by the non-vanishing of the gi bars, okay. When you invert a regular function, okay, you go to when you invert a regular function, the ring that you get is the affine coordinate ring of the basic open set defined by that regular function, namely the locus where that regular function does not vanish. So what you are getting here is the basic open set given by the product of the gi bar. This is the locus in y1 where none of the gi bars vanish, okay, and that locus contains the point small y, okay. That's because none of the gi bars vanishes at y, and that's just a restatement of the fact that none of the gi bars is in the maximal ideal neta, which is where neta is the maximal ideal corresponding to the point small y, okay. Therefore what has happened is that, you know, we have gotten hold of an open set here, alright. We have in fact a morphism of varieties from this open set to x1, okay. We have a morphism like this, and that's because, you see, psi restricted to A is just from A to psi of A, it's an isomorphism, because after all psi is an isomorphism, so the restriction is again an isomorphism, and you see and psi of A is contained in B sub product of gi bar, okay. And mind you, this is this is just A of x1, okay, and this is the thing here is A of D, the basic open set defined by the product of gi bar, okay. And the moment you have a K algebra homomorphism from the affine coordinate ring of one affine variety to the affine coordinate ring of another affine variety, it corresponds to a morphism in the reverse direction, because we have seen this that there is a bijective correspondence between the morphisms of two affine varieties and the K algebra homomorphisms between their affine coordinate rings. Therefore the psi restricted to A, you know, that is a K algebra homomorphism from A to psi A, and therefore it is a K algebra homomorphism from A to B localized at product of gi bar. Therefore it induces a map like this, which is a morphism of varieties, and that is this map, and so this is well, I don't know whether I should give a name to this, so let me write this. I will just write this as induced by psi restricted to A, okay. There is a map like this, and now whatever I did with after all A and B, psi is an isomorphism, whatever I did with A, now I can do it with B, okay. So how do I do the same thing with B? So again what you do is that, you know, you look now, instead of looking at psi, look at psi inverse, okay. So again calculate, let's write out psi inverse on generators of B. What are generators of B? The Ti bar, the Tj bar generate B, okay. So calculate the image of Tj bar under psi inverse, okay. So Tj bar is the image of Tj in this quotient ring, okay, and it's thought of as the element Tj bar by 1 here, and you are applying psi inverse, and you are going to get something here, alright, and that is going to be simply a quotient of polynomials in the S's with the denominator outside the maximal ideal, okay. okay. So you are going to get this is equal to Fi of Fj of S divided bar by Gj of S, where Gj bar is not in the maximal ideal M. You are going to get this, okay, when I take the image of Tj bar here, right. It is going to be an element here, alright, and an element here is a fraction, it is a quotient of two elements, the numerator any element of A and the denominator an element of A which is outside M, and of course elements of A are just polynomials in S, okay, read modulo the ideal of x1, okay. So I am going to get this, and again if you calculate psi inverse of so if you calculate psi of 1 by Gj bar, this is going to give me 1 by Gj bar is, mind you, a unit here, okay, because Gj bar are polynomials which are not in the maximal ideal M, okay. Elements which are not in the maximal ideal become units in the localization at that maximal ideal, and when you apply psi to that I am supposed to get a unit here, okay, and I'll write it as Ai bar Aj bar of T by Bj bar of T, with both Aj bar and Bj bar not in the maximal ideal meter, okay, because that is how units will look like, right. So you are going to get something like this, and if you repeat the same thing that you did for psi inverse, what you are going to get is the following. So what this tells you is that the image of the subring B under psi inverse will go to the localization of A at the product of the Gj's, okay. So you know I am going to have something like this, so I have psi inverse in this direction, alright, and B is a subring here. When I take the image of B, I am going to land in the localization of A at the product of all the Gj's. So let me write that. I have A product of the Gj bar, this is the localization of A at the product of the Gj bars, and this sits inside this, and this of course sits inside AM because all the Gj bars are outside, all the Gj bars are units in this local ring, okay, because they are outside the maximal ideal M, all the Gj bars are outside M, okay. Therefore this localization sits inside this localization, and what is going to happen is that if I apply psi inverse to B, it is going to land inside this. So I am going to get something like this, I am going to get an arrow like this which is just psi inverse restricted to B, okay, because when I apply psi inverse to something here is just a polynomial in the T bars, in the Tj bars, and a polynomial in the Tj bars under if I apply psi inverse I will get a polynomial in the Fj bars by Gj bars, okay. So it is going to be some polynomial in the S divided by some product of powers of Gj's, so it is going to land inside this, okay. And again so again you know, just as in the earlier case you can write psi inverse restricted to B is going to give you map from B, it is an isomorphism of B with psi B, and psi B is contained in A localized at the product of Gj bar, okay, and but B is just the affine coordinate ring of Y1, and this is A localized at the product of Gj bar is the affine coordinate ring of the basic open set where Gj bar do not vanish. So this is just A of D of product of Gj bar, okay. So the moral of the story is that just as in this case you get a morphism from D product of gi bar to x1, you here also you will get a product, a morphism from the basic open set defined by product of small gj bar and into y1. Okay, so the moral of the story is if I translate this psi inverse restricted to B from B to this, I'll get a map like this. I have D product of gj bar, which is an open subset of x1, which contains the point x. Mind you, the point x belongs to this open set. That's because none of the gj bars belong to the maximal ideal corresponding to x. Okay, so x is in the locus of non-vanishing of the gj bars, and the non-vanishing of the gj bars at x is geometric expression of the fact that the gj bars are not in the maximal ideal corresponding to x. Okay, so as a result I will get a morphism like this. I will get a morphism like this, and this morphism is this morphism is induced by psi inverse restricted to B. Okay, so you know I am coming close to trying to find see, basically I want an open subset of x1 and an open subset of y1, and I want an isomorphism between them. So what we have done is we have gotten open sets here and there, and we have got morphisms into the ambient space. We will have to make sure you have to make these open sets smaller to check that you get morphisms between them. Okay, and that's where the big deal comes. So you know now what you do is you I have still things to be inverted on the side of the t's, I mean on the side of the s's, namely the ai's and bi's, and I still have things to be inverted on the side of the t's, namely the small aj's and the small bj's. Okay, so what you do is you go to further localization. Okay, you go to the further localization of a at product of gj bar, and you also take the product over all capital ai bar capital bi bar. This is a further localization, okay, which sits inside this ring. Alright, similarly you go here to a further localization, namely you take B, this is already localized at product of gi bar, but you still have these fellows, small aj bar, small bj bar, which are outside neta. So I can take the product of small aj bar, small bj bar, okay, and that's a further localization, and that also sits inside this. Okay, and what does it amount to? What it amounts to is, here you are going to a smaller open set, namely you are going to the open set given by product of gj bar into product of capital ai bar bi bar, which is open inside this, and x is actually here. Okay, and here you are going to a smaller open set, namely the locus where the product of capital gi bar and product of small aj bar bj bar and y is here.